Hello YouTube viewers, welcome to my show Science Thursday. In today's episode we're going to take a look at atomic clocks. So let's dive right into it. Now first thing you have to understand, what the heck is a clock? Now clock is a measuring instrument. So what does it measure? First it has to measure how much time, basically 1 minute, 1 hour, 1 day, how much time. Then it also has to keep it. Now this keeping part is kind of unique, for time is a fourth dimension. So we have to keep it also, as in how many minutes ago, how many days ago. So we have to keep it. That's why you always hear people say timekeeping piece or timekeeper. Then it also has to indicate it. This is for us basically, and it must be smaller than day, because if you are building a clock that is like showing only 1 day or 1 night, we can see it using sun itself. So it has to be much smaller than that. So even the earlier sundial can show hours very accurately, sand clock also, and this is our modern system. So these are the three core things that it has to do. Now indicate time, that's personal. No clock actually figures this out. We do it on top. Like this is the last layer that we add on. We have to make sure it can measure time and it can keep time. Basically it does not drift over time. So this is the function of a clock. So all clocks have oscillator basically. So what is this oscillator? Basically it's a core and the standard of a clock. So clock is doing something. Clock is telling you 5 seconds have passed, 10 seconds have passed. How the heck it knows? It knows because of oscillator. Now, or what the heck is this oscillator? Oscillator is something that creates a beat regularly. Basically a pendulum is going one way. That's a beat. Basically anything that regularly like with a defined interval does something, we classify it as beat or oscillator. Now it must be independent from influence. What does that mean? Basically if you have a sand clock, it's not like you tilted it, yeah, it's not working basically. And if you have a sundial, cloud comes up here, yeah, your clock says no longer working. So it must be independent from influences. Now nothing is free from influence 100% of the time, but it should not be easily affected by it. At least that's our target. Now it must be reproducible. Now this is core aspect. This is the thing that sun clocks have very well, because no matter where you are on earth, your sun clock will show exactly the same amount of time compared to, like, let's say you are in southern hemisphere versus northern hemisphere. However, pendulums and all that, they struggle with this because there was no length defined, there was no mass defined, and the beats were the calculations for these beats were not very precise. So this is the need of an oscillator. And before we moved into the digital era of quartz crystal, tuning forks were the upgrade from pendulum. Now tuning forks, some clocks do come with tuning forks, but they are now a novelty, but be aware, this was the earliest mechanical electrical system. After that, from tuning forks we went into oscillators. These are tiny quartz oscillator. What the heck they are? Basically they are tuning fork that can be tuned using electricity, because it's a piezo electronic device, meaning if you press it, it gives an electrical signal. If you send it electricity, it expands. So the vibrations of this system can be controlled by electricity. So that's the oscillator for your normal everyday clock. So that's all you have to understand about oscillator. It's something that beats regularly and must be free from influence. So oscillator we have, then why do we have to worry about atomic clock? Now oscillators that we have in general normal clocks, they are very slow. The ticks per second is very low frequency. Basically it's only ticks 32,768 times per second. Now you might be like, okay, that's a lot. Now that's not a lot. I will ask you to remember this. That only translates to 32 kilohertz. Let's say 33 kilohertz. How many things in your life you are familiar with that says more than that? Let's say your mobile phone, it has 2 gigahertz. Let's say your computer, it has 4 gigahertz. So you can understand, we are at kilohertz, we need mega, we need giga. So this is not enough. Basically if you wanted to count reliably, if you stretch the second, you can maximum stretch it to 32,000 parts. Now of course you can do mathematics to guess it, but reliably you can only stretch it to this far with accuracy. You can't go below. Then we come to the core aspect why it's not very popular. It's simply because it's temperature dependent. Basically if you go hot, it will change its frequency. You make it cold, it will change its frequency. It's very dependent on the outside environment. And that's why whenever you have lab instruments, they have something like this, a big container that's containing something. What we call that is like a oscillator oven. Basically you have quartz crystal in them, but it's kept at a fixed temperature. Basically there is a heating element that is always keeping it at 30 degree or 40 degree, whatever the temperature of that specific oscillator, fixed. So that's the only way we can reduce the fudge factor. Now on the fudge factor itself, what kind of fudge factor we are talking about is very high. How high we have fudge factors? Basically you can lose or gain 15 seconds per 30 day. Basically in 2 months you can lose 1 minute. That's not accurate enough for any kind of precision measurement. So, and then on top of that, let's say you did the best you can do, you created a lot of quartz oscillator that is thermally controlled. Now you're getting a fixed standard, and this was used in earlier days of timekeeping, and this whole system was made good enough to 100 kilohertz. Now problem was with that is that no two crystal isolators are the same. Let's say you created isolator in Germany, it's different compared to Sweden. You created in America, it's different. So basically everybody ends up with a different definition of second. That's just not accessible for a global world. For a global world, you have to have fixed second. Everything relies on it, from communication to stock market to everything. So these are the problem with our current technology. Basically we have low frequency with your quartz oscillator, it's temperature dependent, the fudge factor is way too damn high, and two oscillators cannot be the same. So how do we solve it? Here comes the atom. Now atom is the smallest unit of matter. Now you might be like, what about electron, proton? Those are sub elements. Basically not sub elements, would not be correct word, subatomic particle. Basically now you are breaking the laws of behaviors. So the same way we classify cell as the building block of living things, atom is the building block of the life, universe, everything. So you cannot go below it, because if you go below it, you break the properties of the material. Basically iron atom is iron atom, but if you go into electron, every electron is the same. So that's why atom is the smallest unit. You cannot go below it. If you go below it, you are in the building blocks of the atom itself. But atom behavior will change, because electron is same as every other electron, neutron is same as every other neutron. So how do you have any properties? You have properties at atomic level. That's why atomic is the smallest unit of the reality. Now all elements in the periodic table, almost all of them, have natural oscillations. Basically if something happens, let's say you smack iron a little bit, let's say ting, it will vibrate. Let's say you did that with aluminum, it will vibrate differently. You did that with everything in this periodic table. All of them have oscillations. Now many of the elements in this periodic table, especially in this region, basically hydrogen, rubidium and cesium, they have what we call very high frequency. Now right now as I talk to you, the second is defined as vibration of a cesium atom 133. 133 is the isotope, 9.12 gigahertz. Basically, as you can see, now we went from kilohertz to megahertz to gigahertz. That's why we want atomic clocks, because it can stretch 1 second into this is a very large number. It's like 9192631770. So you are stretching 1 second into that many parts. That is why we want atomic things, because it has very high frequency, 9.192 gigahertz. Now here's the on top of that itself is good enough, but on top of that, every isotope in the entire universe will be the same. Basically, let's say you found cesium 133. Let's say you mined it out of India. Awesome. Let's say you mined it out of Pakistan. Awesome. Let's say you mined it out of moon. Awesome. Let's say you mined it on Mars. It's still the same. This frequency will never change. That's why we have to go to atomic level, because atoms are the building block of the universe. You figure that out, it's not going to change. That's why it's always atomic. It's never chemical clock, never compound clocks. It has to be atomic level. It cannot be compound. It has to be element itself, atom itself, because the building properties of the universe come from here. So oscillation itself comes from here. So this is the smallest we can classify a second into. Now if you are familiar with any modern technology, especially with optical computers, you might be wondering 9.192 gigahertz, it's a lot, but there are things that go even higher than teraflops is like terahertz is possible. How do we are doing that? Basically we are moving up the periodic table. This what I specified you, cesium 133, that's a SI unit. Basically people all around the planet has agreed to it. This is 1 second S. Now if you want to figure out what is the vibrations of hydrogen, you can do that. You can Google that. Only difference would be it will say in compared to this is the standard. Everybody is agreeing to this. Basically how we agree 1 meter is this. let's say this is 1 meter, everybody has to agree to it, because if everybody does not agree to it, they will change it. So, and there is no universal second, understand, there is no physical reality, oh 1 second has to be this. It's human rating to it. So we have locked it down to one simple aspect, cesium 133. So as I can already tell you can do that with hydrogen, you can do that with rubidium, and you can also do that with mercury. So that's the atom part of it, that's the oscillator part, how the heck all these things works. Now there are ludicrously complex mechanism at work. Nobody can explain this. You have to study quantum physics to understand this properly. So I'm not gonna try to explain that, but I will try to explain it as a clock, how the heck this clock works. Now atoms are excited using laser or maser. If you are familiar with your chemistry in school, you know, things once they excited, they want to calm down. Basically they want to go from high energy state to low energy state. Now when they do that, they give off photons. Now that photons are unique to every element. Basically like aluminum will give different photon, hydrogen will give different photon. The photons, now all photons are same, but their frequency will be different. Some photons will be emitted in, let's say, ultraviolet, some photons will be emitted in microwave, some photons will be emitted in infrared. So you're getting that. So we excite atoms. Now we excite atoms very precisely. How do we do that? We either use laser, basically laser, if you are familiar with lasers, they have one frequency output, or maser, basically laser but using microwave. Then we excited the atoms using maser or laser, then we let atom cool down, okay, calm down. Now once atom calms down, they do what we call electron transition frequency, basically high energy state to low energy state. Once it's doing that, it's giving off that electricity, whatever that photon is. Now that's specific to elements. You cannot mix hydrogen and cesium. If it's cesium atomic clock, it has to have only cesium. If it's mercury atomic clock, it has to have only mercury. If it's a rubidium, it only has to have that. So that's how we get the frequency, basically like that oscillations, that's how we get it. Now you might be familiar, okay, this so far it's more or less the same as normal oscillator. What's the difference? Okay, it's working at higher frequency, but what it's giving, its accuracy. The accuracy comes that because the property change. This is the reason why we can even make atomic clock. Properties is very easy to monitor, and that is allows us to have feedback loop. What does that mean? Let's say this is the oldest basically maser based cesium atomic clock. So this was very old and complicated. Now what do we have? Let's say for instance rubidium frequency standard, it's used for every mobile tower. So what did they do? It's like they have what we call transition thing. So they will have a lamp that is tuned, okay, it's gonna give light in this specific spectrum. Now they're gonna have a chamber, that chamber is gonna have rubidium gas. So once that chamber is bombarded with the light, it will become opaque. Basically it will become very opaque because it's absorbing it. Now once it become opaque, they will have another sensor that is detecting, okay, no light is coming to me. Now that feedback loop, because the moment you drift even a little bit, either in positive or negative direction, it will become transparent. The moment it becomes transparent, you have the feedback loop. This is what's missing in quartz system. Quartz have no feedback system. All atomic clocks have inherent feedback. Basically this is the nature of atoms. If atom is vibrating at certain rate, it will not change. The frequency output will not change no matter what you do. So the moment you are not getting a feedback that is accurate to what you want, you know you have drifted. This is why we want to rely on atomic clocks for everything, because it will not change. Like if hydrogen atom supposed to vibrate at this, it will vibrate at that. It does not matter how hot it is, does not matter how cold it is. Generally we want to keep it at absolute zero to stabilize, like you remove every other possibilities. But we don't have to do that. Like these things did not have cryogenics, and your rubidium standards also don't have cryogenics. Heck, it has oven system. So yeah, you can get the idea. Like you can remove almost every interference, because atom entirety of universe will vibrate in this exact way if hit in this exact spectrum. Generally we use microwave because microwave tuner is super easy. So that's how it works. You have something that excites atoms, group of atom on a specific element, then atoms cool down. Once the atom cools down, it gives off a signal. That signal is your basically driving frequency. That is your frequency standard. Now that frequency, if it drifts off anyway, that's very easy to detect, and then using that detection method, you provide a feedback. This is a closed loop. This is the core aspect of atomic clocks. I cannot give you a very specific demand because atomic clocks have way too many options. That's why I'm not giving you like this is how cesium works, because there are many atomic clocks. So you have rubidium atomic clocks, which are for mobile towers and basically India is also trying to get make their own rubidium atomic clocks. Then we have hydrogen maser atomic clocks that look something like this. This is used in Galileo's satellite constellation navigation system. Then you have mercury ion atomic clock that is built by NASA. All the links are provided in down below, so do not worry too much about it. And that will be used for deep space mission. Then you have cesium fountain atomic clock. This is right now, as I talk to you, current world standard for second. Like a cesium will behave this many times. Now, how do we count it? Well, you can easily count it. That's not the problem. Problem is how do you average it? So this cesium fountain allows us to average hundreds of atoms very easily. That's the trick part. Because if you can understand this, we cannot make a clock that is more precise than atoms. But even though atomic clocks has been created in 1980s, we don't have absolute accuracy with time. Why? Because the way you count it, that itself is a problematic issue. So all this technology that I'm showing you, they are all working on the same principle. They have something, atom of whatever, like atom of rubidium, atom of hydrogen, atom of mercury, or atom of cesium. They're behaving. They're like, you charge it up, it discharges, it gives you a feedback system. Now that feedback system you can easily rely on to make sure you're not gonna drift for, like, let's say 1 second in 1 million year. However, how do you make it more accurate? You do with multiple atoms. That's the whole trick with this sort of thing. We do it with multiple atoms. We average things out. There are optical lattice system. There are cryogenic system. All this system allows you to do to make sure that refine that measurement. Because be mindful, atom is always behaving exactly the same, but you have to count it. That's the problematic aspect. That's why we will never have anything higher than atomic clock. A, because it's already at the smallest unit. B, if we made the clocks to the absolute accuracy possible with this thing, the clocks start to behave randomly. What does that mean? Basically, if this is how they showed how good those clocks are. You put two clocks, you move the clock up 1 feet, just 1 feet. Let's say you put it on a ramp and you just move it to 1 feet, the time would have started to travel faster. Why? General relativity. Basically, our brother Einstein decided time should not be universal, time should be flowing according to the gravity. So if you have a clock, this is why NASA wants to build this. This is a preliminary stage. Of course, they want to improve communication on space missions, but once we do that, we have to put atomic clocks in space, because right now if you put atomic clock, let's say in India versus atomic clock in let's say China, they will be different. Why? Because tectonic plates are moving differently. So that itself will change the gravity. That itself will change the time flow. Our clocks are that good. Basically 1 second itself start to drift because of this. Now will that affect us? No, hell no, it's not, because that's like 1 second to the power 19th. Now our current GPS standard is 1 to the power 12. Like right now that is for common usage. But you can understand this. Atomic clocks are so precise that it can tell you that, like whether your tectonic plates are moving or not. But we have to put clocks in space for this to work, because you can't rely on the atomic clocks on the surface of Earth itself. We have to put it in Lagrange point. So gravity of moon and gravity of Earth and gravity of sun are cancelled out, and it's like, it's getting very little ripple in time. So this is why atomic clocks are so important for our life, because everything from your 3G communication to 5G communication to your GPS to GLONASS to Bindu system to whatever else that may come, they all need accurate time. This is why we rely on atoms to keep our time. So this was my presentation on atomic clocks. I hope you liked it or learned from it. In that case, please leave a like. If you didn't, don't worry about it. You can dislike it. I would urge you to leave a comment, and please subscribe. Press the bell icon if you're free. And as always, thanks for watching.